Good afternoon. Thanks for coming to this talk. My name is Yong Tang. I'm a CIO lead and the maintainer of TensorFlow project. I work for MobileIron, which is a company in Silicon Valley. This is Yuan Tang. He is a member of Kubeflow and involved in several Kubernetes operators in Kubeflow org. He is also a maintainer of several machine learning frameworks such as TensorFlow, MXNet, and XGBoost. He works for Ant Financial at the moment. In today's talk, our focus is to discuss about large-scale distributed deep learning with Kubernetes operators. We'll briefly cover about the concept in TensorFlow, cover some concept in Kubernetes operators, and also cover some concept in Kubeflow. So before we get started, I would like to briefly discuss about the motivation to have an authorization for deep learning. Many people may ask the question of why deep learning is so special in authorization. There are several reasons for that. In traditional container authorization, you typically deal with stateless containers. Those stateless containers are typically web applications. For web applications, you can easily scale up and down a container without any restrictions. For deep learning, however, there is one big factor. The big factor is the GPU involvement. As we all know, machine learning relies on GPU nowadays. Without GPU, your machine learning will not be running efficiently. But GPU is expensive. That means you have to worry about the ratio of your GPU, CPU, and I/O. If you look at this graph, you can see if your GPU is not properly pipelined, you could waste a lot of time waiting for the data to be transferred from I/O to CPU to GPU, and that's great waste of resource. And the problem is the GPU is expensive. So you want to make sure your investment has been fully recovered when you do the deep learning. If you see the bottom of the diagram, as you can see, with a proper pipeline, you could efficiently utilize your resources, especially for expensive GPUs. So that's why the deep learning has a special need for authorization, and it's very different from the stateless containers like web applications. Another reason for deep learning to have a proper authorization is a so-called distribution strategy. For over the years, people have been proposing different ways of doing distributed deep learning. And the most successful one so far is a parameter server model. In parameter server model, in a cluster, you typically have two types of nodes, the parameter server nodes and the worker node. You typically have one or several parameter server. You also have a fleet of worker node to do all the GPU intensive work. For parameter server, it's a central place for you to update the parameters. Like in the diagram, if you could look at the diagram, the workflow for distributed deep learning with parameter server model is done in this way. Worker node will first do the calculation based on a subset of the data. The partial gradient you calculated will be pushed to parameter server, and the parameter server will grab all the gradient from different worker node, do the calculation to get the new weight. The new weight will be fully distributed to worker node again to wait for the next round of update. So that's a whole life cycle of parameter server model. As we mentioned, the parameter server has been a successful model in the past, but recently people propose and discuss about if there are any other ways of doing distributed deep learning. The most promising one is the so-called allreduce strategy done in the past by MPI community. The allreduce strategy essentially is not a new concept, but it's actually only been used in deep learning community recently. Before we discuss about allreduce strategy, I want to discuss about the reduce strategy first. The concept of reduce is very straightforward. you have several nodes. Let's say you want to do a summation of different numbers stored on each node. So how do you do that? So essentially, you can just aggregate data on different nodes, and with each step, you do a partial summation until you reach the root node, which will give you the final answer. So that's the so-called reduce strategy. For MPI, the concept of allreduce strategy is actually similar. The only difference is that after you get the summation from the root node, you don't stop here. You do additional broadcast to make sure the number is available on all nodes. So it's like this way. You do the summation on each node. You reach the root node to get the number. And finally, you do the broadcast to reach to different nodes so that every node will get a number. So to summarize, allreduce is a reduce plus broadcast model. So one question people constantly ask is, if a Prometheus server has been used in the past, why do we need another distribution strategy? There are several reasons for that. So first of all, Prometheus server require a centralized location to save the data, and this data has to be CPU intensive. A lot of people read the question and say, parallelize on a machine might be different from parallelize in a cluster, and the Prometheus server model might be best fitted to have a multiple process running on the same machine, but not necessarily to do the distributed job in a cluster. So it's kind of controversy to say if Prometheus server is the best approach. But over the years, especially for the past several years, people has invested lots of effort. There are lots of investment over Prometheus server. There are different softwares, different packages and frameworks supporting this model, so it's really hard to throw away. So that's why we come here to discuss about a different distribution strategy for distributed deep learning. If we look back, we discussed about the authorization for deep learning. We noticed there are several characteristics. First, it has stateful metadata. The stateful metadata need to be properly managed in your whole life cycle. We also noticed that we need an authorization framework. Of course, we are here in KubeCon, so we want to discuss about the ways to do it with Kubernetes. If we combine all of them together, the best approach, as far as we could see, is the Kubernetes operators. So in this talk, we are going to introduce several Kubernetes operators for managing deep learning authorization. The operators we are going to discuss are under the Kubeflow project. We will discuss several operators. The TF operator, which is the operator for managing TensorFlow's Prometheus server model. The PyTorch operator, which is used for managing another pretty popular machine learning framework called PyTorch. And finally, we are going to discuss about mpi-operator. The mpi operator here might be misleading because we mentioned about mpi, but really it's actually just MPI allreduce strategy operator. So it actually could be applied to different machine learning frameworks, not just for MPI. Next, I'm going to hand over my microphone to my colleague Yuan. He is going to discuss about different operators and how to do that with Kubernetes and Kubeflow.
Hello? Hello? Hi, everyone. So today we'll focus on these three operators under Kubeflow. So TF operator, obviously, it works with TensorFlow, but not other frameworks. It supports distribution strategies or different backends via its tf.distribute module. For example, MPI, which is the allreduce strategy that Yong talked about, and then NCCL, which is a collective communications library, open source by NVIDIA, and then parameter server strategy that Yong also talked about. And then there's TPU strategy, which will make TensorFlow work well with more efficiently with Google's tensor processing units. And then PyTorch operator, it works with PyTorch. Users can access different distribution strategies via Torch, that distributed module, which includes backend such as Glue, which is also another collective communications library by Facebook, and then MPI and NCCL. Last but not least, mpi-operator supports all types of MPI-based jobs. So for example, you can run all kinds of jobs that can be executed on OpenMPI. So for example, Horovod is a framework by Uber. It supports different machine learning frameworks such as TensorFlow, PyTorch, MXNet, and Keras, which can be either the original Keras or TF.Keras. Users can utilize the Horovod distributed optimizer to run MPI-based distribution strategy. Note that it's only MPI. Let's take a quick look at the different operators. Here we have TF-job, which is on the left-hand side. TF-job is a custom resource definition provided by TF-operator. So all you need to do is to define your TensorFlow replica spec. Here we are defining the worker spec, which includes how many replicas are we running for the worker nodes, and we define the resources that's required for the replicated containers here. And for example, here we are using 4 GPUs, and we execute this TensorFlow script here. On the right-hand side, this is MPI job, custom resource definition provided by MPI operator. It's very similar to the TF job definition. We will just define the MPI replica spec here for the worker replicas. The rest of them are similar, except for this last command to execute inside the container. We run the MPI run command here, and then these Python scripts is a mixed TensorFlow plus Horovod program, which we'll talk about later. First of all, let's take a look at a quick, simple example using TensorFlow to run a basic training locally. So we import TensorFlow here, and then import TensorFlow IO, which is the easiest way to import different datasets, extensions, and file system extensions for TensorFlow. So here we are importing MNIST dataset using the TensorFlow IO module, and then we map each image to images, features, and labels to this particular float 32 type. And then we can take batches of the dataset of batch size 1,000. Next, we can define the TensorFlow model using TF.Keras module. And here we are defining a sequential model, which is a linear stack of different layers, deep learning layers. First, we flatten the input into this particular shape, and then we apply a fully connected dense layer with 512 neurons with ReLU as an activation function. And then next, we apply a dropout here, which means we drop 20% of the input, or we randomly drop 20% of the input to avoid or reduce overfitting problem. And then we apply another fully connected layer with only 10 neurons just to get the different classes here. So once we finish defining the model, we configure the model for training here by specifying this particular loss function and this stochastic gradient descent optimizer. And then we feed the model. We train the model using the data set that we imported earlier and with this many approaches. And then last we evaluate the data, the model using, here is just a very simple example. We just reuse the data set that we imported earlier to evaluate how well is the model performing on this particular data set. This is a raw TensorFlow that can be executed locally. But next, let's take a look at how do we turn this TensorFlow program into a distributed training in distributed settings. So same as before, we import the data set and the model, and then we initialize a mirrored strategy using tf.distribute module. What this does is it mirrors the variables to distribute across multiple devices and machines. We then use allreduce to combine the gradients, combine the gradients across the devices before applying them to the variables to keep them in sync. So simple as that, we just define that we just configure that model with the loss function and optimizer as usual, but within this mirrored strategy scope. Next, let's take a look at how do we use Horovod to run TensorFlow in allreduce fashion. So here we import one additional library here, which is under Horovod.keras library. So this Horovod program would work with tf.keras or the original keras. So same as usual, we define the model data set, and then we define the optimizer using just raw TensorFlow API. But what's special here is that we then apply a Horovod distributed optimizer. We wrap this previous TensorFlow optimizer that we initialized, and then this will configure the distributed training for us using Horovod's defined distributed strategy. We apply we then compile the model to configure the training, and then we define this additional callback for this keras model, which is the broadcast global variable callback. This callback basically broadcasts the initial variable states from rank 0 to all other processes. So this will ensure the initialization of variables is consistent across all workers. For example, if the training is started with random weights, or the training is restored from a previous saved checkpoint, this will ensure the initialization is consistent. So let's compare these two options we have. On the left-hand side is the raw TensorFlow program using tf.distribute module. And on the right-hand side is the Horovod plus TensorFlow program that we just saw. So these boxes highlights the differences, basically. So if we add those additional lines, if we switch this mirrored strategy scope to this Horovod distributed optimizer wrapper, and then add a callback, then we can just switch to use Horovod. And then we can, so on the left-hand side, we can use tf-job to run that particular program. And on the right-hand side, the Horovod program can be executed using mpi-operator. So record, sorry. And next, let's briefly talk about how do we use Horovod with PyTorch. So so we just do like usual normal PyTorch program. We import the PyTorch module, and we use PyTorch's own data loader to load the data set, just as very similar to previously we used TensorFlow IO to import the data set. And we initialize an optimizer using PyTorch optimizer. And then similarly, we apply a Horovod distributed optimizer on top of the PyTorch optimizer so that we can use the distributed strategy defined in Horovod. And then similarly, we broadcast all the variables using this Horovod that broadcast parameters. Note that this function is available under Horovod.torch, but that's the only change you need to make in order to run PyTorch using Horovod. And here we are very similar to the TensorFlow plus Horovod program. We use the rank 0 process as a root process, so we can so we initialize the rest of the processes using the same variable states. And then here we do under this nested for loops. We iterate the data and run the PyTorch training here, step by step. Okay, let's recall TF job versus MPI job. These are the only differences we need to make in order to run TensorFlow program under TF operator or MPI operator. But note that here the API version v1 alpha 2 for MPI job is still a work in progress. This is something we work with the community to ensure the two different operators or even more operators such as PyTorch can be, their API can be standardized and similar to each other. So these are the only changes we need to make in order to switch one operator to another. Something we are working on. So all these commonly, all these code, all these reusable components from different operators, for example, TF operator, PyTorch operator, MPI operators are copied over or are refactored in this Kubeflow common repo. This also includes common and standardized API spec, and there's also a base job controller interface so that new operators can just inherit and implement using the utilities we have in this repo. And there's also testing utilities in Kubeflow Common. So this is something we are working hard on to make sure the APIs are standardized and the components are reusable. So for example, we are working on, at Ant Financial, we are working on XGBoost operator, which will inherit directly from this common operator.
I think that's it for today. I'm just wondering, anyone has any questions?
Sure if you support TPUs already and parameter servers for TPU. So 2 questions in here. If you support TPUs already, Tensor TPUs are already supported.
So I think the question is about TPU. Okay, that's. So first of all, TPO is only, we talk about TensorFlow, we talk about TPO, and you probably could hear TPO aloud from Google guys. TPO is essentially designed and released by Google, and that's only available on Google Cloud. So it's very much vendor specific. So if you use, I would say if you use TensorFlow on Google Cloud, you probably can experiment and use TPO, because that's, as far as I know, there is a very good support from TensorFlow team to make sure all the algorithms are available for TPO. But if you try to, for different reasons, for cost reason or for your company policy reason, you decided to use a different cloud vendor like AWS, or if you decide to deploy your own GPU fleet, then TPO is not going to be, not going to be the best choice. And also I would like to point out is that at least for TensorFlow, not all the algorithm will always run on TPO, but TensorFlow team has spent a lot of effort to try to make sure TPO is very close to a first-class citizen support. Yeah. Any other questions? Oh.
Thank you very much for the talk. Very technical. Really liked. I was wondering, among the frameworks you mentioned MXNet, and as far as I understood, you would support MXNet using Horovod for sure. But as far as I can remember, MXNet has a built-in MPI support for distributed computation. I was wondering if you could integrate natively MXNet into Kubeflow with any specific MXNet operator, maybe.
Okay, so I think the question is, we discussed about different distribution strategy and discussed about different frameworks, but we probably didn't talk a lot about MXNet, and your question was, MXNet actually have support of distribution strategy built in. So you're just wondering if this one is something we consider.
So yeah, it's very similar to TensorFlow and PyTorch, which have their own built-in support for different distributed strategies. But so the answer is totally up to you to whether to use the built-in distributed support or not. There's also Horovod support, Horovod integration with MXNet, so that you can run MXNet using Horovod as well under the standardized Horovod MPI. So it's just like very easy to change, to switch one framework to another. So so sometimes if you want to do different POCs on different frameworks, that might be helpful.
Maybe I can add a little bit more comment. If you have been involved in different machine learning framework, you probably noticed that there are a lot of ways to do the same things. For example, in TensorFlow 1.x, if you want to build a model, you could use TF curves, TF estimate, TF layers, and TF slim. Eventually, I would like to say is certainly you have the freedom to select any framework or any way to build your model or build your distributed deep learning framework available. But basically you want to stick with the majority of the users, because that's, as far as I know, many frameworks are not truly in production use or not truly widely used, which actually you may encounter some issues if you use some less known frameworks or less used frameworks. So that's my suggestion. Okay, any other questions? Okay, I guess that's it for today. Thanks everyone for coming to this talk. Have a great day and enjoy your stay in Barcelona, beautiful Barcelona.